welcome to Covalent Compounds, Chapter 6. Now that we are masters of the ionic compound, we can compare them to covalent compounds, just a different type of bonding. However, there are some similarities. Any kind of bond is a good thing. Atoms need to come together with the goal of getting a full outer shell of electrons. The Octet Rule. There we go. Usually we want a full outer shell of 8 valence electrons. Most atoms need to bond. They don't naturally come with a full outer shell of electrons. The only atoms that aren't interested in bonding are the noble gases. If a bond is a good thing then, if having a full octet, a full outer shell of electrons, is a good thing, by that we mean it's stable. The atom is now more stable with its full octet. Stable is always associated with low energy. The atoms are always at a lower, more stable energy level once they are bonded. Which then means that when the bond forms, energy is released. Forming bonds will release energy. In a chemical reaction, we can rearrange atoms and make new bonds. Any chemical reaction should be accompanied by some type of an energy change. When you form new bonds, energy is released. The atoms are at a lower, more stable energy level. On the flip side, if you want to break a bond, energy must be absorbed. To break a bond, we have to add energy. Because again, these atoms want to be together in the bond. In the bond, they have full octets. So if I want to disrupt that peaceful bond, I need to add energy. So there are some chemical reactions that are endothermic, that require energy. Energy is required to break bonds. So those are kind of important, 3 and 4. Energy is released when a bond forms. Energy must be absorbed in order to break the bond. Okay, so there are some similarities, things that are true of any type of bond. Here are the main differences. And this first one, this is really the most important. Ionic bonds form from the transfer of electrons, but covalent bonds share electrons. Our goal is still to get a full octet. Now, in a previous science course, you may have drawn atoms looking something like this. I don't love this model. There are some inaccuracies, but I'll get over myself. I'll deal with it. Let's do, I don't know, how about fluorine? Fluorine has 9 electrons. Did you ever draw atoms kind of like this? Where there's little rings, and then you put like a pair of dots together that's supposed to represent 2 electrons. Here's the second energy level. There are 7 valence electrons in the fluorine atom. Set. So it looks something like this. There, fluorine. And again, now at the time they probably didn't tell you why you pair them. And now we know because electrons come paired in orbitals. Why are there only 2 electrons in the first energy level? Oh, because there's only an s orbital available. It can only hold 2 electrons. The second energy level could hold a maximum of 8, 2 in the s, and then 2 electrons in each of the p orbitals. We're really only concerned with the electron structure, so we're going to disregard the nucleus. And for purposes of kind of visualizing bonding, I'm okay with this. Now let's say we bond that fluorine to something like sodium. Sodium is a manageable element. Sodium has 11 total electrons. Here's 2. And then here's 8 in the second energy level. There we go. And 1 valence electron. There. 1 valence electron in the third energy level. The 3s1 electron. This would represent sodium and A. Okay, so again, bonding is about getting a full outer shell. In this case, fluorine wants one more electron. Sodium has one extra. It's perfect, a match made in heaven. Sodium can transfer this electron to fluorine. That fills fluorine's outer shell with 8. And if we get rid of this one, then the outermost energy level in sodium is now the second, and the second is filled with 8. By transferring the electron, both atoms can get a full octet. Ionic bonds. Covalent bonding is a little different. Let's do, how about 2 fluorine atoms? So here's a little fluorine. 1, 2, and then 3, 4, 5, 6, 7, 8, 9 total electrons, 7 valence. Let's do another fluorine. There's 2, and here's the 7 valence electrons in fluorine. 7. All right, so 2 fluorine atoms. Fluorine, fluorine. All right, so everybody wants a full octet. Now, in this case, transferring will not give both atoms an octet. I mean, we could take this lone electron on the second fluorine and try to transfer it over to the first. The first fluorine would get an octet, but the second fluorine is worse. He goes from 7 valence down to 6. He's going in the wrong direction. The fluorine really wants to gain one more to achieve his full octet. But in this case, transferring will not satisfy both atoms with an octet. So we share. In covalent bonding, we share an electron pair, and that pair counts for both atoms. This way they can both get an octet. Visually, this is what I'm thinking. When I picture in my head covalent versus ionic bonding. Covalents share the electron to achieve the octet. Ionics transfer the electron. Other little differences, some of these we can look at in the lab. Ionic compounds exist as a large crystal. Covalents exist as separate molecules, individual molecules. When I think about a crystal, an ionic crystal, again, this could be like the sodium fluoride. Sodium is +1, fluorine is -1. You'll have this repeating pattern of oppositely charged ions. So these charges would alternate positive, negative, positive, negative, positive, negative, positive, negative, all throughout the crystal structure. It's a sodium, fluorine, sodium, fluorine, sodium, fluorine, in a repeating pattern, a very organized crystal structure. Okay, so a couple things that we should mention then. These ionic crystals have strong attractive forces. Attractive forces, which makes them often solids. When you think about it, these ions are oppositely charged, opposites attract. All of these ions are highly attracted to each other. If you have strong attractive forces and the ions are real closely packed to each other, these ionic compounds are often solids then. Covalents are a little different. We could have like fluorine, F2 fluorine. It's just a bunch of fluorine molecules that are just kind of hanging out. There we go. There's no organized crystal structure. If it's a solid, the particles are just kind of randomly smushed together. They're close to each other, but again, they're not in an organized crystal pattern. Or we can also put these can be any phase, solid, liquid, gas. Most gases are covalent compounds because, again, we should make note, there are no ions. There are no ions. There are no charged particles. I'll put that down too. No charges. The charged ions result from the transfer of an electron. The donor becomes positive, the acceptor becomes negative. We're not doing that here, we're sharing the electrons. By sharing the electrons, we do not form ions, which then we do not have charged particles. You'll just have these little molecules kind of hanging out. And depending on their arrangement, they could be any phase, solid, liquid, or gas. Another property that we'll test for in the lab, number 3, ionic compounds will conduct electricity when dissolved in water, which is kind of important. Number 1, in order to conduct electricity, you need moving charges. You need some kind of moving charged particles. Well, enter in the ionic compound. Ionic compounds are composed of charged ions. The only kicker is that in the solid phase they are not moving. These solid crystals are very rigid structures with lots of attractive forces. That's why we dissolve them in water first. The ions separate. So for example, in salt water, if you dissolve salt in water, the sodium and chlorine ions just separate from the crystal. So you have individual sodium ions swimming around in the water, individual chlorine ions swimming around in the water. If you evaporate the water, the ions are attracted to each other again, and they go back to the original solid. So we dissolve the ionic compound in water first to separate the ions, and then we should be able to test that solution, and those moving charged ions will conduct electricity. Not the case with covalents, because again, the covalent compounds don't contain ions. There are no charged particles. They will not conduct electricity. Another property that we'll test for in the lab is number 4. Because the ionic compounds have such strong attractive forces, strong attraction between those oppositely charged ions, ionic compounds tend to have high melting and boiling points. Strong attraction. Hello, strong attraction. There we go. We'll try it in the lab. We'll try melting some sodium chloride. It's probably not going to happen. Those oppositely charged ions are just too attracted to each other to separate. But covalents, again, with no strong charges and no strong attractive forces, will have lower melting and boiling points. In the lab, we'll also test burning them. The ionic compounds don't melt, and they really won't burn either. The covalent compounds should melt and burn in our laboratory with a reasonable amount of energy from a Bunsen burner. The last one, 5. Without doing any kind of lab tests, you could just look at the formula and figure out if a compound is ionic or covalent. The ionic compounds will always have a metal bonded to a nonmetal. Ionic compounds. Metal, nonmetal. Because we said the metal is always positive and the nonmetal is always the negative ion. And you have to have one of each. For an ionic compound, you have one positive, the electron donor, and one negative ion, the electron acceptor. Covalents are all nonmetals. Covalent compounds, all nonmetals. And someone had asked about this earlier. For example, let's say we're looking at a compound like nitrogen and oxygen, NO2. Here's a common compound. And they were like, well, how does this work? Because on the periodic table, nitrogen's charge is -3 and oxygen is -2. They're like, you can't have this compound. Oh, you can. But you could not have this compound by transferring electrons and forming ions. Because you're right, in an ionic compound, both nitrogen and oxygen need electrons. But you don't have to worry about that if it's covalent. In a covalent compound, they share their electrons, and sharing electrons will not create a charge. So I mean, it's kind of nice. You get to take a little break from being obsessed with charges and making the compounds neutral, like the ionics. Since the covalents don't form ions, you don't have to worry about their charges. You don't have to worry about making them neutral. They'll share electrons to obtain their full outer shell.